In this lecture, we're going to briefly discuss the concept of data structures. Up to this point in this class, we've been talking about objects that are capable of managing other objects, and we've called these collections. And one collection object basically has the role of, creating and destroying, or at least managing a bunch of other objects. And we've been using just really basic arrays, or either the ArrayList class in Java, to manage the internal structure of our data for these collection classes. What I want to do now is take some time to introduce you to some additional data structures. And if you find an interest in this lecture, then I would encourage you to continue on and take some additional courses in data structures. And those of you that are going on to do master's level work and even PhD work in computer science will find that you will do a lot of work with data structures and possibly even define some of your own over time. So what are data structures? Well, it simply is a way of stating that we are organizing data in a way that we can efficiently compute that data. And the example that I like to use here is, let's imagine that we have a dirty house, and you could just kind of dive in and grab one item at a time and just start processing and cleaning the house. But oftentimes what people will do is they'll go through that mess first, and they'll make a stack of books, a stack of, say, dirty laundry, a stack of dishes, and then once they've kind of organized the mess, they'll go ahead and they'll actually clean the house. So when it comes to organizing data, we want to put it into a shape or a form that makes it easy for the situation that we're in, or the algorithms that we're using to efficiently process that data. And that's really what data structures are all about. So let's talk generally about data structures for a little bit, and then we'll look at some specific examples of some very basic data structures. So the one nice thing about data structures is they provide a standardized approach for data organization. In other words, most of the programs that you write are not forging new ground. You'll be kind of repeating a lot of processes and functionality that have done in the past. And data structures provide kind of a standardized look into well-known ways to organize data that have kind of proven themselves over time. There are new data structures being formed all the time. Google and companies like that are managing large amounts of data are always going to be pushing the envelope and having to come up with new ways to manage data. But the ones we're going to talk about today and that you'll need to learn first are kind of those foundational data structures that are just kind of classical data structures within computer science. A couple things that we need to know about data structures is that they have different advantages and disadvantages based upon the usage. So we're going to look a little bit at some data structures in this lecture, and some of the things that we'll need to talk about are the efficiency involved with those data structures. So sometimes organizing data in a specific fashion takes a lot of processing power. It might take a lot of memory. Well, is it worth, taking that processing time and taking that memory to actually organize the data, or is it quicker to just leave the data unorganized and kind of process the data as is? So there's always this balancing act between the algorithm you're using to process the data and, the amount of time it takes to actually organize that data. So if it takes a long time to organize the data and then a short time to sort it, to search it, then that's probably a really good thing. But you really need to weigh the algorithm in question versus the data structure you're using and the application that is at hand. A couple other things is that we're going to talk about the concepts of specific data structures, but this concept of a data structure exists separately from how that data structure is implemented. Let's take a look at that in this slide. So when I mean implementation, what I'm saying is I've got listed on the left, and we haven't talked about these yet, but a couple of different types of data structures. I'll talk about a little bit about a list and a tree and a graph and a queue and a stack. And underneath most of these data structures, they can be implemented using either an array or what's called a linked node structure. So we're talking about kind of the abstract data type of the data structure, the abstract data structure, the concept of a list, the concept of a tree, but how that actually gets put into code is, again, this kind of concept of abstraction. Like we, don't necessarily have to know how it's being implemented at the lowest code level. Now, if we are the ones that are writing the code to the tree code or the graph code, then obviously we're going to need to take into consideration whether we want to build it, implement it using an array or a linked node structure, and then obviously you would need to understand the ramifications of both. And again, that's where a course in data structures really comes in handy. But let's kind of expand on what I mean by having an array-based implementation versus a linked node implementation before we start talking about some data structures. So when I say list-based, I'm just kind of using an array. This idea that we have an indexed set of data, and it's contiguous blocks in memory. And again, the best way to think of a list-based implementation is it's really an array-based implementation. Like whether we're talking about a queue or a stack, or say like a complete tree, this idea that the data is stored in an array. Okay, so the back end, we're treating the data in an array in a specific fashion, so it works like a queue, it works like a stack, but underneath it's still an array. And we kind of did this with the collection that we wrote, right? We built a soda machine or some equivalent object that manages other objects, and we abstract out this idea that, yeah, it's a soda machine, but underneath it all, it's really just an array, and we're just adding and removing stuff from the array. So these types of data structures are that same concept, whether we're using it, whether we're conceiving this as a tree or conceiving this as a queue or stack, underneath there's just an array. So what does this look like in memory? It's going to look just like an array. And we'll expand on this a little bit more as we talk about different data structures. So we've got an index, got a value associated with that index. Pretty straightforward. Well, what does it mean to be a node-based data structure? Well, and this idea that node-based and list-based, array-based data structures are interchangeable is completely true in most cases. So a lot of times when we implement a data structure, we're going to need to decide between an array-based implementation and a node-based implementation. So what's a node? In the case of Java, a node is going to be an object. In a program like C, a node would be what's called a struct. But the reality here is a node has two components. It has what I'll call a payload, which is the data, and then it's going to have a reference, and that reference is going to point to another node in the list. So each node is a self-contained object, and each node knows of the next node that's in front of it. There are also, multiply linked data structures, but right now we're just talking, I'm kind of demonstrating what's essentially a linked list here. But this node idea is that we have data and then a reference to another node. Okay. The one thing about node-based implementations is that they do consume more memory in that you need to have the overhead and processing involved with having multiple objects. But what's kind of cool about node-based implementations versus array-based implementations is that they work really well if you're going to be adding and removing data anywhere in the list. So if we think of an array as having indexes, right, like 0 to array.length, if we're constantly adding stuff in the middle of 0 and array.length, or we're adding things to the beginning of the array where we might have to move everything back in the array, a node-based implementation is going to be quicker because instead of having to actually shuffle around a lot of data within the array like we've done in examples in this class, we can actually just swap a few references and insert a node more quickly. And again, the advantage to say using an array-based implementation, or why we might choose an array-based over a node-based implementation, is that we're maybe just constantly adding data to the end of the array, which is actually a really quick operation, right? Because everything's in front of it, say from like index 0, doesn't move, but things towards the end of the array just get added onto it. So this idea that we have one implementation that utilizes a traditional array. We have a second implementation that utilizes this concept of nodes that carry a payload and have one or more references to other nodes. And again, the cool thing about this is that node-based structures can grow dynamically. So again, just like an array has a dot length, right? Array dot length that is it's a immutable concept. In other words, like once we create an array, it can never be made bigger. This idea that a node-based structure is really only limited by the size of the memory on the computer that we're dealing with, and it can grow and expand dynamically. We don't have to necessarily create a new array, copy everything over, or swap references like we've done in the past. So there's a dynamism that's appropriate in a node-based structure, and there's also this idea that it's easier to add and delete data to the middle of a node-based structure. So let's look at this in operation. Here's what's called a linked list, and this is a kind of an analog to an array. This idea that we have an object at the front, and if you can see the cursor kind of floating around that first node. So this would be the same as index 0 in an array, but in the idea of a linked list, there really is no concept of indexes in general. So this contains, in this node, the payload of the string JSON, and then a reference to another node object. And what does that, oh, and I forgot to change the names on all these node objects, so they're all going to be JSON, which is hopefully not going to confuse you. But let's say that this was like Larry, Curly, or Mo. So the idea here is that it's going to point to this node. This has a payload of JSON also, and it has a reference that points to this node object, and then finally it points to this node object. And we know we're at the end of a linked list because we hit a reference that is null. So in other words, we can simply add or delete nodes to this list simply by repointing these references at different nodes. Can this get confusing? Can this break. I mean, obviously you don't have the compiler enforcement that you have with an array and this rigid structure that's set up with arrays, but this flexibility is really powerful, and this idea of having one node using links, in other words, pointers, reference variables that point to other objects, or in the parlance of, say, like C or C++, pointers from one object to another is really powerful. So this is what a linked list is. It's similar to an array. There's a definite front, a definite back, and any given number of objects. It's composed of nodes, and each node has a component of data and a reference to the next node in the list. There's also things like doubly linked lists that not only keep references going forward, but they keep references to the node backwards in the list. And so you can have these references go anywhere, right? They're just references to objects. Let's talk a little bit about variations in lists. To make this a little bit easier, I've gone ahead and put these together as array-based list variations. Two variations on the list. We've got this concept of an indexed, ordered set of data. So we've got the traditional concept of the value JSON being at index 0. Again, we could convert this easily into a linked list. We can apply rules to the top of these list variations and expand on them. So this idea of a list, which is an indexed set of data, if we apply some rules to that indexed set of data, we have a new type of data structure. So in the first-hand example, we have what's called a stack, which is a first in, last out data structure. And what that means is we're only ever going to add and remove data from the top of the array. In other words, the 0 index of this array. So any new data as it comes in is going to be put on top. All the old data in the array is going to get pushed down. So what that means is, in this example, the first thing that was added to this array was Curly, the second thing added to this array was Larry, and then finally the last thing that was added was Jason. Now when we take data out of this to enforce the rules of a stack, we're going to take Jason out first, then Larry, and then Curly. Stacks are analogous to if you've ever been to a buffet and you take that plate off of the spring-loaded stack of plates at the end of a buffet. Chances are there's a plate at the bottom of that stack that's been there since the place opened, right? Because all the new plates just get stacked on top of all the old plates. Or the other example of a stack would be your laundry basket, right? The older clothes are at the bottom of the laundry basket, the newer clothes are at the top, and chances are if you have to steal something out of your laundry basket, most people steal it from the top because it's technically cleaner. So again, we've just taken a list, this basic data structure of an index set of data, and we've applied some additional rules to it. Hey, you can only add and remove data from the 0th element, or the head node of the linked list, and we can call it a stack. Next up is a queue, and if you've ever waited in line for a movie or any other thing that deserves waiting in line for, you are familiar with the concept of a queue. It means first in, first out. So if you show up in the morning at 2 a.m. to get the new iPhone or the new Android phone or the new Palm phone or whatever you are waiting for, this means that this piece of data was the first thing added to the list. Larry was the second person who got there at 2:15 a.m. Curly maybe got there at 2:30, and it works just like a queue at the movies, right? New people are added to the back of the line, and then once the store opens, the first person in the store is the first person at the front of the line. So this is a perfect analog to the real-world concept of a line or a queue. Again, this is just a typical list, an index-based set of data that we've applied some rules to, like first in, first out. And that's what's really cool about this, right? Like once you apply some rules to these really fundamental data structures, like an array, and then further on as you learn like a linked list, you can have a lot of power. And again, it's this idea of standardization, this idea that the compiler, that your code is actually going through and enforcing these rules for you. I mean, you could always just say, hey, here's an array, everybody treat it like a queue. But if you build an object, there's a queue object, and then you have methods that enforce this concept that the first item in is the first item out. Then you can never have broken code, right? Like there's no way that somebody could cut into line or break the rules of a queue because your object enforces those rules. So these are just some basic data structures, right? This list-based, link-based kind of implementation. Then we can have lists on top of that. We can have stacks and we can have queues. So what are some other data structures? Well, let's talk a little bit about trees. And trees are this concept of, it's a different way of storing data, and it's often done so that we can easily search and get through that data much more quicker. Probably the most common example of trees in existence today would be databases, because most database programs, now I know things are changing, but database programs are basically just highly abstracted trees. So when you're working with Oracle, you're working with optimized, highly abstracted trees. Actually, you're working with a lot of high-tech stuff, and things may have changed since the old days and what's being implemented on there, but it's essentially where these things started. And so what's a tree? Well, it's pretty simple. We've got a node structure that has a payload. In this case, it's another string like Larry. And in this case, I have a binary tree. It contains two references, and one reference goes to what's called its left child, and another reference goes to what's called its right child. Well, what happens when we follow the reference to the left child? Well, we've got Curly, and my tree, by the way, is not sorted because I just realized I didn't sort it, but Curly's got a left reference that points to the node that contains the string JSON, but the right reference doesn't go anywhere. And what I've shown you here is that we actually have a node-based implementation of a tree. You can actually do an array-based implementation of a tree, but it has to be what's called a complete tree for that to be, functional in an easy manner. So a tree, again, is a different way of organizing your data. And basically what happens is with most tree structures, we maintain the data in a somewhat sorted fashion. So somewhat sorted, not sordid. But we maintain the data in a sorted fashion so that we know that, say, everything down the left side is going to be less than the item above it, and everything down the right side is going to be greater than the item above it, although I kind of broke that rule with JSON here. So it makes it quick and easy to sort through the data. In the lectures this week, we talked about some searching algorithms. We talked about the binary search. The binary search takes a linear set of data and searches it by constantly breaking it in half. There's a thing called a binary tree, which actually maintains the data in a sorted fashion that allows, and essentially that sorted fashion is a way that implements or reflects what happens within a binary search. In other words, we're already maintaining the data in a binary sorted fashion, so that all we have to do is a linear walk from the top to the bottom, and it's a quick way to get to the data that we want. Anyway, without going too much into it, a tree is just a different way of organizing data so that we can easily get at what we want. So let's look at one more before we're done. Another form of data structure that you're probably already familiar with is a graph, sometimes called a map, because if you look at Google Maps, Google Map is a graph, right? It's got a bunch of destinations, and those destinations are connected by roads. And in a graph, what we usually have is a bunch of data nodes, and those data nodes are connected by references. And I've actually left the references off here just for to declutter this slide so that it's not too difficult to see what I'm talking about. But the idea here is that each node has what's called a bunch of edges, and the edges are what connect to the different nodes. So unlike the tree that we just looked at, right, we have a very strict rule that each node has only 2 references, and each of those references goes to a new and unique child. When we're talking about a graph, in this case, I've got it set up so that each node can have any number of edges, and those edges can be pointing to any number of nodes. So you'll notice like Larry is connected to Curly, and Curly is connected to Mo, but notice to get from Larry to Jason, there's no direct connection, so I have to walk through or go through the reference Curly to get to Jason. There's really no rhyme or reason about how I have this connected. I just wanted to kind of demonstrate what a graph is and show you that there are different ways that we can organize our data. And the other thing, you'll see this a lot in video games for pathfinding. You'll see this if you use Google Maps, this idea that, when you enter in, how do I get from Larry to Jason? The Google Maps algorithm will weight the edges and determine, is it better to take this route to get there, or is it better to take this route, or is it, is this route out of commission, and should it go from Larry to Curly to Mo to Jason? Should it take you really out of your way? But this idea that we can, again, organize data in a fashion that makes it more computable for the situation at hand. In other words, what is our application? How do we want to utilize the data? What are our computing resources available? Do we have a lot of power, a little bit of power? And how do we want to organize that data so that it can be appropriately and efficiently worked with within the context of the problem that we're trying to solve?